Now we're going to move to a type of model that tries to describe the relationship between two variables. And in particular, we will, in this video, motivate where this model comes from. So this is the second, basically, chapter in our modeling discussion. The first chapter looked at constant models and loss functions, and now we're going to use that framework to introduce what's called simple linear regression. So last time we were just looking at a model to try to capture the distribution of a single variable. And at the end of the day, our model was just a single summary statistic. We got either the mean or the median, depending on the type of loss function we chose. More commonly, we're going to create models that try to explain the relationships between multiple variables. So here are some scatter plots looking at the relationship between X and Y. And you can see we have different relationships we can just see visually here. This top left one looks what we call random noise. The top right one looks like we have a strong linear relationship. This one definitely has some kind of relationship, but it definitely looks more quadratic and not linear. And this one does look linear, but we see that we have this kind of spreading out behavior happening, like hourglass, in terms of how the data points are distributed. So just visually looking at these, we can see we would want different models for these different scenarios. So we're going to start with the simplest case. And before we do that, we're going to think about what statistic we've already defined that helps us capture a relationship between two random variables. And one of those statistics was correlation. For two random variables, X and Y, this was the definition of the correlation. It was a value between -1 and 1, and it gave us a sense of how linearly related the variables were, and also an assessment of how spread out they were around a line. So we can actually calculate this for a sample or for a set of data points. We can calculate the correlation as follows. So if we get a set of data, x1, y1, up to x sub n, y sub n, we're going to calculate the means, standard deviations for that data, and then this is the actual calculation behind the scenes to get the correlation. So you sometimes will see this called Pearson's correlation coefficient. And as just a side note, it's related. You can get back to covariance by taking the R and multiplying it by the standard deviation of X and the standard deviation of Y. Okay, now we're going to look at a toy data set. Actually, it's not even toy. This is a historical data set that is actually pretty famous. This is something that was collected. This data was collected in the late 19th century in England by Sir Galton. And he basically was the first data scientist in the context that he coined the term regression towards mediocrity to describe the result of his model for this data. He collected heights of parents and took their average height and then collected the height that their children grew up to be, so the child's adult height, and was interested in seeing if he could come up with a model that used the average of the parents' heights to predict what adult height their children would have. And what's interesting about this, we're going to see a basic model that he did, but his analysis is actually still useful today. There's a nice paper I'll link in the footnotes here that shows that his approach actually beats some modern genomics approaches. And so it's nice because it's so simple and yet does capture the trend in the data. So what we're going to do is to motivate the model that we will use for this data, we're actually going to do what's called a graph of averages. And this is not the only way to get to a model. I just like to use it when I'm introducing models in this class because visually I think it gives some justification for the type of mathematical model we're going to derive. So imagine you wanted to take this data and come up with a prediction, predict the value of y for any given x. One thing you could do would be to bin the x-axis, and then for example, all the data points that have the mid-parent or the average parent height right in this interval, we're going to take the average of all the y values, and that's going to give us some average y, which is basically plotted right there in that yellow dot. And I could do this for each bin, and I could see the general shape that I get from these averages. And it turns out for this data, we get basically a line. And so that is actually one justification, one motivation as to why we're going to come up with an actual mathematical model that's just based on a line. Okay, so that is my motivating example. And now let's describe models that have, or let's come up with a model that's based on a line. So yes, we're going to go back to our y equals mx plus b that you may know and love from previous schooling years. This is the equation for a line. X is my independent variable, y is the dependent variable, theta naught is the intercept, theta 1 is the slope. And so a question we could ask is, what is the best line for a given data set? And so in other words, I'm trying to figure out the best slope and the best intercept for a data set. The x value, we're not considering those parameters because that comes from the data. We directly observe them. What is considered a parameter in this case are the slope and the intercept. And we are going to come up with the parameters that appear best. And right now I gave you a purple, a green, and a red line. And I'm just asking you to eyeball those three. And if you had to pick one of those three lines to model the overall trend in this data, which one would you pick? And I want to point out it's not that obvious just by eyeballing it here. This is why we are going to need some actual mathematical formalism around what we mean by best. We're going to pick some criteria that we use to help us judge our best fit. Okay, so I'm going to just go over some notation that we'll be using as we formulate this idea. So the first is you have the actual data points, x1, y1, x2, y2, that you've observed. So those are just x sub I, y sub I. Y hat are the predicted outputs. So that's going to be whatever our model predicts. Basically, if I give it this x sub 1 input, what y output would it predict? What height of the line would it predict? Then I have the model parameters. So that is, in this case, it depends how we've set up the model, but we've basically taken the constant model and then just added a new term that depends on our new predictor or our new feature here. And then we're going to have the estimated parameters. So once I use data to try to come up with my best slope and intercept based on some criteria, so we have to define best. But once I do that, then I'm going to get an actual values for these. Okay, and these are, so I'll put hats on them because they're estimates based on my data sample. If I took a different sample of data, I'd get a different estimate for the theta naught and the theta 1, which is why I put hats. So again, based on your interpretation, which are the optimal parameters for this model, I gave you three choices. You can take a minute and just read your own reasoning, pick which one you think would be, quote, best. I'm going to leave you hanging here because, again, best is going to depend on how we are measuring our loss. And so that's going to lead us to thinking of our framework of the modeling process. We've just chosen a model. And eventually we'd like to fit the model. We want to find our, quote, best slope and our best intercept. But to do that, we need to choose a loss function. So stay tuned for which of those lines will be, quote, best for the next video. And in the next video, we'll discuss how a loss function will affect our answer.